Fire it up, see what we got. 3 years later, come on. Did we lose somebody just then?
He reconnected.
Okay, good. Yeah, we have some Discord issues, especially in y'all's dorm area. On occasion, I'll get somebody that says, hey, your mic doesn't sound right, but yet everybody else is hearing it perfectly. So, you know, we do see problems with the internet in your area. I do not know what the remedy is, but I think what they're looking at is because with this COVID and that, they are trying to get internet in there on a consistent basis where mainly for school. So,
Okay, I can hear you now. I can hear you now. It's working.
yay!
Sorry about that. I even joined the chat 15 minutes early.
Yeah, I saw you in there. I'm well aware of that. I see just about everything that happens in Discord for some reason. I don't know. You're okay. You're fine.
All right, thank you. I just didn't want you thinking I was being late. I was excited for this.
No, I had seen you in earlier, so I knew something. You know, people have technical difficulties, and that's what I try to find out. If you're having technical difficulties and you're late to class, that's the reason why I say you might want to get to Discord early so you can prevent those technical difficulties. When I see you in Discord, I know that you're here, but you know, that's the reason why I take a verbal, hey, are you here type deal, and you could either do chat or, you know, sound off on your mic. It's just, we've had people come late to class, like really late, and then I've had people that come to late that just did not have a valid excuse. In fact, I had one student come late. The last one was he showed up an hour later. Oh, what they did with him, I have no idea. All right, so enough of the bad part. Let's get to the good parts. We're going to be looking at Nyquist theorem. Picking up from 1 Bravo. We're almost completed with 1 Bravo, but we got to talk about the Nyquist theorem. If you go online and you look up Dr. Nyquist, because that's who it is, he's the one that came up with the pulse code modulation technique of changing analog to digital. So he came up with this, how are we going to sample this? In other words, we're going to sample this analog waveform. How many times do we need to sample it per second? And what he came up with was this nice rounded figure because it fit within the audio spectrum. Normally, most people talk between the 300 hertz to 3K hertz. And of course, there's people outside that range. You know, not very much outside that range. But you do have people who have deep vibrato bass voices, and that would go below the 300, you know, once in a while. And then you would have people who have that very high soprano voice and can go above the 3K. So what he said, you know what, I'm going to make this 4K. That's the audio. And we're going to sample it twice the amount of time to get samples per second. So within 1 second, he's going to sample it 8,000 times. Now, the formula is considered 2 times the highest audio frequency. Notice I said audio. Now, with that in mind, we don't need anything greater than 8K or 4K for audio. We don't need anything greater than that because we're not into making a stereo system. We're into communicating voice to each other. So that seems to be a nice rounded figure. And the reason why, if you went over 4K, then you start getting into what's called fold over distortion. Now, with that in mind, how many people have ever played with the program Audacity?
I have a little bit.
Okay.
A little
All right,
bit,
sir.
All right. So when you are saving your MP3 files, or if you're going to save it as a WAV file, there's certain techniques that go to it, especially when you're saving it to the MP3 files, because there's this thing that you can save it as far as the sampling rate. If you go through the long list, you'll see at the very bottom 8,000 times a second. Nowadays, you can save it as high as 320K a second. Now, hear me out on this one. The more you sample, the more it's going to sound realistic from the original, or whatever you're producing, whatever the sound you're reproducing, it will be very close to that original. But the more you process it, in other words 320K, you got to have the processor work it. So with 8K, you don't need a big processor, especially when you're dealing with software defined radios. And that's the whole thing. We don't need, this awesomeness of 320K to make it sound just as close as you can to the original. We just want to communicate. So 8K is good enough. So that starts with the PCM that we're getting ready to look at. We have this particular style. There are 3 steps to it. You got sampling, quantizing, and encoding. Now, with the sampling, we have something called pulse amplitude modulated pulses, which is PAM, not Peter Pan, but PAM, the spray that you spray in your little skillet before frying an egg, if anybody's ever used it. And what we're going to do is we're going to sample that analog signal 8,000 times in 1 second. It's going from the horizontal view to a vertical sampling. So horizontal is the sequence of events that's happening, and each one of them is equal. So you can take 8,000 into 1 second, and you get probably about 125 microseconds for each pulse. That's pretty doggone wild. So when you're doing this, it's going to take that pulse and it's going to hit that line that it's on with each one of those sequential horizontally, and then it's going to go vertically and measure that pulse. Now we're going to take that pulse and we're going to put it into a decimal. I like to call it a value. Ones and 1, 2, 3, 4, all the way up to a positive 127 and all the way down to a negative 127. This is called a quantization table. It looks similar to a graph paper. There's 127 lines to the positive and there's 127 lines to the negative. Looks like a graph paper you had back in grade school or high school. It is for me. So when you look at this is considered a uniform quantizing table. So we're going to take these pulses, we're going to apply it to the table, and give it that value. Again, it's equally spaced horizontally and vertically. You see that we have a negative 127 and a positive 127, and there's a reason for it. This is part of that 8-bit word. So let me go back to that 8-bit word. No, it's not going to give it to me. I need to get it back up in there. But let me go back to this 8-bit word. And you can see that 1, 2, 4, 8, 16, 32, and 64, if you add all of those together, you get 127. Okay. We know that the 127 to the positive and 127 to the negative, but we got some issues here. We'll get to that in just a second. Now, we're going to put all these pulses on that paper for uniform, And what we got a problem with is when we put these pulses and they fall in between the lines, we have what's called a quantization error. And with that quantization error, the computer knows that I need to go either round it up or round it down depending on where it falls within that area. So like if it's 4 or below, it's going to round down. If it's 5 and above, it's going to round up. Just like your general rounding is. Well, that created a lot of quantization errors. So how do we correct for some of the quantization errors? Well, what they said, or Dr. Nyquist said, hey, you know what? Most of people's voices are within this certain range. So if we squish all these 127 lines a little bit, you know, they still have to have, hey, from point A to point B, 127 minus 127. We can't change the distance between these. But what they did do is they took most of the lines and squashed them all together to where most of the human voice is. So that way, we eliminate a lot of the quantization errors. Now, granted, we're going to have quantization errors when you got somebody who's got a very high-pitched voice or a very low-pitched voice, because it's not going to fall on one of those lines that are farther apart. You're going to have more quantization errors. But it eliminates most, the key word there, most of the quantization errors. So what we do with everything else now, that is called non-uniform quantizing back here, where we squish those lines together. We have uniform quantizing using this type of table. You have more quantization errors with uniform than you do with non-uniform. That's the correction. The next, or the last step, which is step 3, encoding, we're going to convert it to a binary or a 8-bit word. Well, I told you from 1 to 64 gives us 127, but that 8-bit, well, what do you do with it? Well, the 8th bit decides whether or not you're above the 0 line or below the 0 line in either the positive or negative. And that's where you end up with the 255 on that 8-bit word. So let's apply it. So you can see the encoding table off to the left, and we put it onto a box to give us that 8-bit code. You can see that we use the first 7 digits to apply our, negative 120 or the 127, but the last digit, the far left, would be whether we're positive and you're negative. And you're going, oh crap, we got zeros gives us positive, negatives are ones, logic ones. Don't ask me. I don't know why. My logic would say, hey, to give us a positive number, a logic 1 would be better. But those are the engineers. I don't know the reasoning behind it, even though I've looked it up as to why. One of these days, I'll finally come across it. Or if I find an engineer, I'll ask them. So there you have it, the 3 steps. There are sampling, quantizing, and encoding. Just remember, if you have quantization errors, hopefully you're going to switch from uniform to non-uniform quantizing to eliminate most of those quantization errors. Frame period. Now, frame period is what we talked about earlier, and it gives us the time it takes for one of those frames to occur. In other words, we have 24 channels, and we're going to sample that whole frame of 24 channels and find out how long it takes to give us that frame period. So in other words, we're going to sample 8,000 times a second. We're going to get 1 over 8,000, which is the reciprocal, and you're going to get 125 microseconds. So the time it takes to sample all, for one frame, from channel 1 to 24, you get 125 microseconds. That's a pretty big frame, in the wonderful world of electronics. So now you get what's called the pulse modulated sample period. And what happens is now I need to know, okay, it took me this long to sample all 24 channels. Now I want to sample just one of those channels within the multiplexer. So what I do is I take the frame period I just got and I divide it into the number of channels is going to be divided into it to give me the pulse modulated sample period and tell me how long it took to do one channel. In our case, it was 5.28 microseconds. So it was to sample one of those is 5.28 microseconds. To sample all 24 was 125 microseconds. Everything in this particular case is dictated upon the number of channels. So if you don't know what the multiplexer channels are, in other words, do I have a 16 channel, do I have a 20 channel, do I have a 24 channel, do I have a 50 channel, whatever it is, unless you figure out how many channels you got, you can't get your pulse modulated sample period. So in a nutshell, big, which is frame period, small is pulse modulated sample period in sampling one channel. So we've gone through general multiplexing terms, data relationships, types of multiplexing, modes of TDEM, demultiplexing, signal formats, and analog to digital. And by the way, the PRIC 150 does do PCM. Any questions?
No, sir.
No, sir.
A lot of information, isn't it?
Yes, sir.
Oh, we're not done yet. We are not done by any way, shape, or form yet. We have all the way up through 5 alpha to do before you take the test. We're just getting through 2 alpha. So we're going to look at identify basic facts about network, bandwidth, management, equipment, and we're looking at, you need to answer 28 correctly in order to pass the test. Yeah, if you're dealing with anything in the SATCOM area or wide-banded equipment, you're probably going to have to deal with some type of multiplexing equipment and dealing with bandwidth. When we had the FCC 100 here, and when it was out in the field, you literally got to program your signal format along with how much bandwidth you could use and so forth and so on. We're going to look at bandwidth allocations, network infrastructure, transmission media, carrier system concepts, and hierarchies. Let's take a look at these. We have 4 different bandwidth allocations: conventional, demand assigned, dynamic, and time of day. Conventional means it is fixed, but just like synchronous, if you don't use it, you'll lose it. This gives you an idea of some that are taken up and some that aren't. You're missing about 128 out of that 256. So basically you're losing 128K out of it. We look at demand assigned. This is the exact amount for the user. The nice thing is this is basically how the internet works. So whatever your carrier provider is giving you is what you get. Now I'm here in Ocean Springs, and we have AT&T. You can also get Sparklight. Sparklight is the 1 gigahertz gigabit system, whereas AT&T, I got I think it's 25 down and 5 up, and that's the highest end of the commercial side before you start getting into the business side. I could get 100, but no. I'm still waiting for fiber to be put in here. Half the city has fiber, the rest of us don't. I don't know what the problem is. They've been telling me for the last 3 years they get fiber in here. But let's take a look at what I'm running. I'm running not only this with Discord, but I also have approximately 4 to 5 computers running at any time on this network. I have my cameras running on an intranet. I have my heating and air conditioning thermostat running on the internet, intranet. I probably have a phone or two that's on the Wi-Fi, which I always tell them not to. It's just sucking up bandwidth that you don't need. But just to give you an idea, that's what I'm running. Do I get, that's the exact amount I'm allowed to have, but there are times where I can exceed that amount, and there are times where I don't exceed it. So it goes back into this little pot, so to speak. So if you have 256K of total bandwidth, and you have 3 users that only total up to maybe about 120K, well, think about it. If you're not using yours, it gets put into that little pot just in case somebody really needs it. So during the time frame, I might be running more than 25 meg. You know, I might be running 50. Who knows? But if I exceed it and someone else needs it, then they're going to, what they call, throttle me, get it, back to my original purchased price of 50 down and, not 50 down, 25 down and 5 up. So there you have it. This is how the demand assign works and how the internet works. Too bad Boingo isn't like that, right? Next is dynamic. This one is where they max out the data rate in idea or hopes that not everyone will be on the line. This is basically how the trunking system works, which is LMR style. So you can see that we've exceeded the bandwidth. So if everybody gets on and is trying to max out their bandwidth, you're going to have problems. And this is where a lot of the issues are happening, and this is my opinion. When you do something like this, and my guess is Boingo does it at times, I don't know. I couldn't tell you. But I do know that if you're paying for it, you should be able to get what you pay for. Next up is time of day. The big thing about this one is, anybody's ever watched The Lone Survivor, when they're trying to contact back to the base, they have specific times to do that. I think there was like a 15-minute interval where they were allowed to talk on a certain time frame every day, but you know, they were never able to because of their radio person really didn't understand that you can't transmit in the trees. Get it? So time of day, if they had, you know, if they had a clear shot, they would be able to talk. And with this time of day, you have the priority. No one else does. Why? Because they set that time frame up for you. So it just gives you an idea how these, you know, time of days restrictions are. Next up, networks. Network is when you're talking interchanges. In other words, you've got several servers talking to each other, and you know, you're taking everybody's data back and forth throughout the world. Does anybody know about the submarine cable?
Yes.
This would be an awesome place to put it in there just to give you an idea. But the submarine cable is back in, way, way back. I want to say, trying to think here. Early 1900s, all the way up to probably about the 70s, 80s before they started replacing it. But they would lay cable all through the ocean. For example, that's how you were able to talk from England to America, is those submarine cables. They were all wired. Now they've replaced them with all the fiber optics. And if you go out on the internet, you will find the submarine cable chart. In fact, this is how networks, or you're able to talk to somebody, let's say in Europe, right now if you wanted to, using either Discord or TeamSpeak or any of those. Let me get into block 7. Where is it? Where is it? There it is. Submarine cable map. Kind of pretty, ain't it? So there you have it. You can talk, and for example, when I'm on World of Tanks, on occasion, I'll get shifted to the South American server. I hate that. Why? Because the North American server, at any given time, we're anywhere between, when I get on it, anywhere between 10,000 to 30,000 people online. When I get on the South American server, we might have 2,000, and they put bots as tanks down there. So you can see that that's a pretty far distance, and my ping rate would probably be around the 100 to 300 area. So that's some delay there. And it can be detrimental to your win rate if that's the case. Now, I've played on the European server, and let me tell you, those are some really competitive individuals. But again, you're dealing with a ping rate of between 100 and 300. Whereas the North America one I play on, which is Central, you have approximately a between 50 and 70 ping rate. So, the lower the ping rate, the better your chances are of doing what you want it to do. So there you have it. That's a submarine cable, and you can take a look at, other places where it's going all over. And I'm still trying to figure out this island right above Greenland. I need to do research on it. It's in the BERT Sea along with the Greenland Sea and the Norwegian Sea, but it's up in the Arctic. One of these days I'll get enough motivation to look it up. So there you have it. That's a submarine cable. A lot of networks are on there. Then we look at something called the EIA Standard. Now, back when computers started becoming really prevalent and people wanted to use them to communicate more and more and more, we had problems. For example, if you bought an Apple computer back in the, let's just say, 80s and 90s, you ran into a problem where you had to use an Apple printer to print things. You would need an Apple disk drive for you to expand your, the media and so forth and so on. So if you bought a PC, you would have to buy that manufacturer's PC. Like Dell, you would have to buy a Dell printer and so forth and so on. You couldn't mix and match. Well, what happened was these EIA standards and the RS standards and a couple other things decided that, hey, we need some interoperability between the manufacturers so we don't have a monopoly. So thinking about this is how they came up with this one standard. So now an Android phone can talk to an Apple phone and, so forth and so on. You can use Google for any one of those things. And, Apple computers can print out on a HP printer and so forth and so on. So it just gives you an idea of where we were and what we're doing now. Just like when you guys went through trunking and they talked about the APCO 25 standard. Let's take a look at these. Yeah, for the most part, the Apple proprietary hardware is a pain. But then again, what do you like? Do you want a PC that you can pick and choose what you want to put on it, or do you want to get an Apple and just call it a day? So, it depends on what you want it to do. EIA 230, this is the beginning. I'm not sure if anybody's ever had to deal with a dial-up modem, but this is the start of it. Makes that distinguished.
Dial-up is terrible.
Yes, and if you've ever heard the sound of, when it's dialing and the bing, you know what I'm talking about.
It's terrible.
Very. So what they came out to now is they've talked about EIA transmission lines. So you're going to have balanced and unbalanced. So the balanced one is where we have a twisted pair. That's what it is. And on each of those lines, we're going to send a separate signal. It's going to be the same signal, but with a little twist to it. One of them is going to be 180 degrees out of phase when you send it. So the line driver at one end, the transmit end, is going to take the signal, duplicate it, and flip one of them 180 out. So when it gets to the distant end, because most of your twisted pair do have noise on it, when it flips it back into, the same waveform, you're going to have all this noise with it, but what happens is it cancels the noise out. This is the precursor to noise canceling headphones. So how does the noise canceling headphones work? Well, it takes the outside noise, looks at the inside noise, and twists it, again, 180 degrees out of phase. So when it gets put back together, twisted it back in, you have the regular sound versus the sound with the noise, and voila, it cancels it completely out. That's how the noise canceling headphones work. This is the same way. So we look at something called unbalanced line. Now this is the cable or the coax that you're dealing with. So if you had spark light down here on the coast, that's what you're going to get. You're going to get a coax cable coming in on your line there. So you look at an unbalanced line, it's a center conductor, and the shield is grounded. For those of you who ever ripped apart one of those coax cables, it's basically the same way as the BNC cable that you guys have. Did you guys do that in Dolan Hall where you pour one or put a cable end on it?
No.
We did not, sir.
No, sir.
Only myself and Smith went to Dolan, I believe.
Okay, so I guess
I went to Dolan as well.
okay. Did you get to do that?
Yes, sir.
Did you do Cat 5 cable too?
Yes, sir.
Too as well.
Yeah. That's an experience that I wish we could continue here because, believe it or not, that's a tough thing to do when you're out in the middle of the field and you have no idea how to do it. No idea. So I highly recommend that you figure out what you need as far as tools, probably about $20 to $30 worth of tools, and get you some connectors and work on it if you need to. Nowadays, it's all going to fiber, but hey, it's a lost art. Next up, physical characteristics. You're going to have to deal with a DB connector when dealing with the NSM tomorrow. You're also going to have to deal with a lot of signal formats. Now, that DB connector, if I'm not mistaken, is a 50-pin DB connector, so it'll be a DB50. And it looks like a D when it comes right down to it. So take that D and put a whole bunch of pins in it, and there you go. And if you had one of the netbooks, you can turn it on the side there. I don't know if it's the right side or left side of it, but it has I think it's a DB25 on it, and it's mainly for a monitor. And here's something unique. I don't know why it's in there, but we do have this equipment just to give you an idea of what's still out there. We do have equipment that has something called negative logic. With negative logic, this is crazy. I dealt with the OJ314, which has negative logic on it, and it's really hard to stay straight with it. You spend more time troubleshooting it because of the negative logic, because you think, oh, well, this should be a high. Nope, it's a low. Well, wait a minute, why is it still working? And you got to look back and you realize, oh, crap, it's negative logic. Oh, and it just adds time to the troubleshooting. That's all they're trying to tell you is you may run across it. EIA 530, this is what you're going to deal with in the NSM lab with the DB50 connectors. It'll say it on the back of the case, EIA 530. It also has some that'll say EIA 630, I think. I think it's 630. But this is how we go from the 56K to faster, real quick. Next up, we have two things called a DTE and a DCE. We're going to be using our NSM as, I think, with the computer as a DTE. I think it's been a while since I did it. They also use it as a DCE if possible. So what does that mean? It means that the DTE, the key word in DTE is terminal. Terminal is a source. In other words, like a computer, I send it out to the destination, and it's also the destination, which is the destination. So a computer is just like that. When you get into DCE, it's the communication device that you're sending that digital information to, and it's going to convert it into a signal to where it can send it out farther than what a digital signal can, because digital signals don't go that far when you compare it to AC. So, and if you've ever seen the History Channel with what was it, Edison and Tesla, I guess, the AC wins out because you need bigger equipment for DC to generate that type of voltage to, to light your lights and electricity and so forth and so on. Wow. So next up, we have four types of transmission media. We got the twisted pair, we got coax, fiber optic, and wireless. Twisted pair is pretty obvious. Phone lines are like that, the old style. In fact, my mom still has it. Probably about 5 or 6 years ago, she still had the rotary phone, for those of you who know what that is. So twisted pair, now she's on fiber. Go figure. She's in a rural area, and I can't even get fiber to my house. And she's had that fiber for the last 2 or 3 years now. So evil. Next up is coax cable. This one, again, it's a, when you compare twisted pair, this is balanced. When you compare it to coax, coax is unbalanced. Why? The shield is grounded. All the data is on the center pin. Fiber optic uses light. Does everybody know that light is RF? No. Yeah, it's in the terahertz. So we're putting information on light. Did you know that you can hear RF? Oh, yeah.
No.
Yeah.
So if you take a look at the international frequency spectrum, you will see from about 3K to 30K is part of the bottom of the RF spectrum. So from about 3K to 20K, I can hear probably up to 17K, hang it up after that. So that's actually RF. So you can hear RF and you can see RF, the light. So just going to show you, take a look at the international frequency spectrum and you'll see and hear. So those are two visual or two sensory items that you can use for your RF technique. And then lastly, we have the wireless. This is pretty much your IP networks, your Wi-Fi, your phones, things like that. It's easier not to be tethered to a wire, even though wire is better. Is better when it comes to having links, because Wi-Fi can be interfered with. Lastly, we have a couple of units here called the DSU CSU. The DSU is the customer loopback. You'll see down here where it says alternate mark inversion. It is not self-clocking because it is RZ bipolar. Again, it's the customer side of the network. Now, why are we even introducing this? Well, number one, you may have to deal with it. And number two is if you're dealing with, equipment in general with the Air Force, you may come across this. Normally, the DSU and CSU are a box and both of them are in it. What's its use? Well, let's pretend that I lost my internet. I call AT&T up and say, I lost my internet. Well, let's do some checks. The first thing they're going to do is they're going to use the DSU and they're going to start trying to find out if they can talk to my internal through the router. So if they can talk to the router and find out everything is good, then they're going to say, oh, gee, the customer is right on this one, and we don't have to send anybody out to the customer side. Why? Because they're going to go to something called a CSU, and they're going to check the network side, and they're going to do loopbacks. So they're going to check and see if that is okay. Now, this one uses something called RZ bipolar with zero suppression. And again, you're going to hear terms like B, Bravo 8, Zulu Sierra. That's the North American for a T1 line. A Bravo 60 Sierra is a T2 line. A Bravo 30 Sierra is a T3 line. And when you get into Europe and Japan, then they go Hotel Delta Bravo 3. You're going to see these things, at least the first two, which is the Bravo 8 Zulu Sierra, as well as the Hotel Delta Bravo 3 on the NSM. I think it's a T1 E1 line. So pay heed to what we're talking about. CSU, DSU. Remember, DSU is the customer side. CSU is the network side. I get a lot of problems, people getting those two confused because they think the C in CSU means customer. No, it does not. The network side. D, Delta, is for the customer. C, or Charlie, is network. So however you figure to remember that, keep it in mind. Next up, we have hierarchy. The idea here is we take and use a standard 24-channel multiplexer, and from there, we start building rates. And as you can see, what a DS1 line, or a T1, T2, and T3 line, like I was just telling you about the bipolar with zero suppression, you can see that we get into faster rates here. So let's take a look. This is probably the best one I've seen out on the internet as far as building the multiplexers. You can see from channels 1 through 24 is a standard multiplexer. We take that and go into a T2 multiplexer, which is going to take 4 of those 24 channel ones and put them all together and get a faster aggregate at 6.312 megabits per second. We're going to take that and we're going to use 7 T2s into a T3 multiplexer, and we're going to get 44.736 megabits per second. And then we're going to run 6 of those into T4 and really go up the scale. So you can see the hierarchy that we are building here. But you'll notice it only has 2 T4s going into a T5, and let me try to explain that one. They have something called superscripts that get generated when you get up to that area when building multiplexers. Excuse me, multiplexer hierarchy. And the reason is that these superscripts are considered errors. So they just come out of the woodwork on there because it gets so quick. So they generate these errors, which creates problems as you go up the hierarchy. But by getting into fiber, they don't have too much of this problem with building the hierarchy, because now you run them into servers. So we've looked at bandwidth allocations, network infrastructure, transmission media, carrier system concepts, and hierarchy. Any questions on what we went over?
No, sir.
All right, let's go on to the next one, which is 1 Delta, identify basic facts, principles, capabilities, limitation of multiplexing equipment. So we're going to look at the NSM, but I'm going to quickly go through it because we're going to look at the tech manual on this thing after I get done with 2 alpha. This is the Nodal satellite multiplexer. We're going to look at purpose, functional description, operational characteristic, and the configuration. So this is what it does for the purpose, which is multiplex and demultiplex. Aggregate rate is 52 meg. It has 2 operational modes, legacy and enhanced. That means old guy like me, new guys like you. Get it? So newer equipment's considered enhanced, older equipment's legacy. Here is the input ports, max data rates. We'll go through those in a little bit. This is what the back of the case looks like. Now, if you look above me, you will see the 3 cases in room 116. By the way, that's the room you'll be going to tomorrow. Room 116. You'll see 3 cases on a table. The far left case houses the NSM50. You'll notice there's something right above, another picture above the NSM50. This is called an iDirect. It is off to the left-hand side. It looks like an old TV monitor when you are looking at it from afar. Well, it's not. All those are cards right behind that picture frame, so to speak. And then when it's turned on, it gets really noisy in there. But the 3 cases, when they're turned on, it gets noisy with that one too. So my suggestion is if you have a tendency for, sensitive to noise, I suggest that you get some earplugs. Not earbuds, not earphones, but ear protection devices. So if you're sensitive to that, you can use that. You can't use anything that's going to be playing music or anything else. Not authorized. Okay? You'll notice that on the red square is 12 NRZ ports. They are all D connectors. You'll notice that the T1E1 ports, which is all green, there's 6 of them, kind of represents the old VGA style connectors. And then you have the 2 hissy ports. Those are unique, in my opinion, because the cables are different. Still represents like a D connector, but it's different. And then, of course, he has right above it, disregard that. I was looking at the hissy ports. The blue CDI ports are like cannon plugs. The hissy ports are what looks like to be the old plug-in D connectors. Oh, geez, I'm trying to think of the darn names of them now. But there's only 2 plugs that's going to go into multiplexers. All right? So that's what you have. You'll notice that you'll see like underneath that red, bottom red square, it'll say EIA 530. That's where you're starting to see some of those ports. This is the extract we're getting ready to go over after we complete 2 alpha. Notice it's all tied into the TSC 179, which is in block 9, multiband terminal. So there you have it for the NSM. That was 1 delta. Let's go to 2 alpha. 2 alpha is saying that identify basic facts, capabilities, and limitations of a bit error rate test set, better known as a BERTS. We're going to be using the BERTS in conjunction with the GUI laptop. When I say GUI, that's Graphical User Interface. That's what the Golf Uniform India acronym means. We're going to describe what a BERT does, and then we're going to look at the HST 3000, which is what you're going to be using tomorrow. This, better known as the BERTS, you can see what it does. You can do it alone or alongside the traffic. The idea is you want to look for bit error rates. In other words, how many errors is it generating? Perfect systems don't have any errors, but I've never seen a perfect system. When you get in there, you might see this turned into a perfect system because it's self-contained. We look at the HST 3000 because that's what you're going to be using as the BERTS. If you were to purchase this off of eBay, you would pay approximately $3,000 for it brand new, and they still have them in stock. However, this is a piece of equipment that has exceeded the manufacturer and what it wants to do as a newer, improved one. Just like with TVs, you buy a TV, it's old already the moment that you grab it and put it in on your TV stand. With the HST 3000, it was purchased back in, I want to say 2010, but it still works today. We don't need anything new because we don't do anything different with it. It is rugged. You can beat the crap out of. I've accidentally dropped it and it still works. Don't do that, by the way. It is battery operated, or you can use the power supply that goes with it. These are the 3 test modes. Count them, 3. That it does. It has DTE emulation. Where have you heard that term before? It has DCE emulation. Again, where have you heard that term? And then, of course, monitor. So it just gives you an idea of what the HST 3000 is doing for you. Voila. Now, before we get into the NSM Tech Manual, this is probably about 15 minutes long. Does anybody have to go to the restroom? You want to take like a 5-minute break real quick? Are you guys even here?
No, we're good.
Oh, yes, sir.
Good.
All right, let's go.
Up to you, sir.
All on me? That's not good. Yeah, I got 3 hard drives. Okay, so when I pull this up, you'll see it's the NSM 50 Nodal Satellite Multiplexer. Multiplexer. iDirect is a modem. 2 different entities. We're going to cover the modem later. So with this one, what I've done is I've highlighted specific areas for you to literally pay attention to. My question is what is the cost of paying attention? Is it a quarter? Is it a dime? Is it, $50? What? The first place I got highlighted is the scope. This describes it. You'll notice it says the sentence there, it says a lightweight synchronous, have you heard that term? Time division multiplexer, again, another term that we've covered. And it interfaces to satellite modems and group interfaces to group equipment. So, goes to the satellite or goes to the user equipment. General functional description. This is explaining what it multiplexes and what it demultiplexes. Notice about halfway through it says the mic and the little and symbol and Charlie can be accessed either directly using this particular protocol or through the use of GUI, graphical user interface software. You're going to be accessing it through the GUI tomorrow. You're going to be monitoring the NSM alarms, diagnostics, and LEDs on the front panel. Here you go, where it says Control Computer Interface. We have RS-232 or 422 DTE. Where have you heard that term again? Signals. Bravo says, again, 3 pins are required for DTE or, another DTE. When using the GUI, software configurations can be stored and retrieved on the computer's hard drive. The computer is what you are programming the NSM with. And of course, Delta tells you that anytime that you have this stored in the NSM, when you turn it off and fire it back up, it's going to retain the information. Next up, 1.3.1.5 external signal interface descriptions. I'm going to try to explain this to you. Bravo. NRZ group port data clock signals must be balanced RS422. You have legacy mode and you have enhanced mode. So if I asked you, according to what this is indicating, I asked you what is the max data rate for the NRZ group port, what should your answer be? By the way, can you see this?
Yes, sir.
Yes,
Okay.
sir.
And we're only on Bravo. What is the max data rate for the NRZ group port? No takers?
1,152 kilobits per second.
Okay. Is he right?
Yes.
Wouldn't it be? I think that's 8,448.
I would be more inclined to go with that than the other. Let me explain why. Listen to the question. What is the max data rate for the NRZ group port? What that means is look for the higher number, whether it's in legacy mode or enhanced mode. But 99.99999%, it's going to be enhanced mode because that's the newer equipment. So I would go there and look for the higher number there. So that's 8448 kilobits per second or 8.448 megabits per second. So you see how that works. Listen to the question and figure out what the question is asking you. If I had asked, hey, in legacy mode, what is the max data rate? Then you would be correct in saying 1152K. But in this case, I asked what's the max data rate for the NRZ group port. In other words, what is the max that you can get out of it? So we look at Charlie, T1E1. Notice it says bipolar. Number 1 says T1 AMI or Bravo 8 Zulu Sierra. That is self-clocking, by the way. That's zero suppression. Bipolar 8 zero suppression at 1544K. Never mind, that was you. Okay, good. Did you hear that little part there, Bakken?
No, sir.
Okay.
It's that.
No problems. All right, the T1E1 must be bipolar. Bipolar, where have you heard that term? Well, we just talked about it back in signaling formats. The T1 says AMI, alternate mark inversion, or Bravo 8 Zulu Sierra. Zulu Sierra being zero suppression, Bravo being bipolar. So what it's telling you, this is self-clocking at 1.544 kilobits per second or 1.544 megabits per second. The E1 throws us a little curveball. It says AMI or Hotel Delta Bravo 3 at 2048K. Well, let me try to explain this again. It is self-clocking, but there's a difference. The T1 is a T1 line in North America. The E1 is if I'm going to Japan or Europe, because they work things a little bit different. For example, over there, a high ping rate means that everything is working well, and that's the way their computer systems are set up. Yeah, confused the crap out of me. But when we're using it here in North America and going there, we still keep our ping rate. I don't know what the interface is for it. So, again, we're looking at signal formats and all this other stuff that we just covered, and here it is in the NSM tech manual. The group modem, CDI, conditioned die phase. Is that clocking or self-clocking? Wait a minute. Is it clocking or not self-clocking? Takers? Got a 50-50 chance.
Clocking.
It is clocking, yes. It relies on transitions for its clocking. You have the legacy mode and enhanced mode, and of course you can see the max data rates on those. Echo. This is the EIA 530 or 613. Sorry, I thought it was a 30. So that's EIA 13. This is a HISI, high speed serial interface. That's what the HISI means, not a HISI fit or anything like that. You can see that when I ask you the max data rate for the HISI is 52,000 kilobits per second or 52 meg. So here's the question. What is the max data rate for the NSM 50? Max data rate for the NSM 50. Anybody?
52 megs?
Yeah, 52 meg. 52 meg. Why? Because that's the maximum data rate when you look at the NRZ T1E1 group modem and the HISI. So it takes prevalence. So that's the max data rate of the NSM 50. That's pretty easy, wasn't it? You know, sometimes it's the easy questions that kill you. All right, so this is the peripheral equipment that you'll be using tomorrow or tonight, this afternoon. This afternoon? No, tomorrow. Grief. Losing days. All right, so you have what's called a tough book. The power and the information that you're going to be using for the GUI. It is a tab system, so it's like Windows. You look at the tab and you click on the tabs to whatever you want. This is the purpose of equipment that we just went through on the prior slide. I think it was 1 Delta. I love this picture. Why? It's very simple but to the point. You got all the data streams from the users and channels and that goes to the NSM, and then it links it to the satellite and sends it up to the satellite. Bird in the air is what they call it, and then it relays it back down or repeats it back down to the receiver, and then of course it demultiplexes it and sends it to the users on the other end. Wow, it's that simple. Here's some more functional operation, and whenever you see the MUX and DMUX, you can pretty much apply it through any time that we have a multiplexer. MUX means we're multiplexing. DMUX means we're demultiplexing. Picture's worth 1,000 words. If you can't remember the ports, you have two places to go. You got chapter 1 and then you got chapter 2. Ports are telling you the data rate. Chapter 2 is telling you how many ports there are. You got 12 NRZ, 2 HISI, 6 T1E1s, and 6 CDIs. Love it. And of course, I really like this one. This is your network configurations. And it explains like the point-to-point, the hub spoke, the mesh, and the hybrid. One of the better ones I've seen out there. I just pointed out. You got modes of operation, not to be confused with legacy and enhance. This is telling you again how many ports there are. And if I'm not mistaken, it says any 12 of these ports can be active in MUX or DMUX configuration at one time. There's a 26 available ports, but you can only be 12 of them can be active. And again, it tells you how many of those you have. Talks about the internal and external loopback. No worries there. The next place is order wire. Remember, we talked about order wire being a ancillary function, which means that we always have, maintenance does, that is, always has something separate from the aggregate. This separate thing is how we're able to communicate to the distant end when we have problems, instead of having to go through a computer and one of the user ports or something like this. This is the back of the NSM. It's internal to the case, not to be confused with what's on the back of the case. Just goes through and shows you all the little things. Now, this is the front where you can see it. It has, I think, 12 LEDs, 6, 7, 8, 9, 10 LEDs, 11 LEDs, I think. Yeah, 12 LEDs, looks like. And it goes through each one of them and explains what's happening. Remember that order wire? Well, number 6 is where you would plug up that handset and talk to the distant end. Number 5 is an error indicator. When you are doing your programming of the NSM and you think you got everything completed, if that error light is illuminated, you're not finished yet. 99.9% of the times you forgot to apply all the programming. When I say apply, there's a little button that says apply programming at the bottom of the tab, or actually the window that itself. You have to apply it, then go in and take a look at the alarms. If all of them are green and you still have a red error light, then your NSM might be the problem. But not NSM, the BERTS might be the problem. It's probably not syncing up, or you don't have it connected correctly and it's just giving you an error. So these are just little hints that when you get to the NSM and what you're going to be doing. For the most part, we are through with this, and you can see that this icon down here, it looks like a little satellite dish. That's the icon that you're going to use. And normally the first window that pops up will be this one. You go into General, I think, and click OK, and it will boot you right up into something that's pretty darn close. In the tabs, it doesn't show you what's in the programming software on this. So we have finished all we need to finish for the day from objectives 1 alpha through 2 alpha. Is there any questions? Because I know it's a bunch of info. No questions?
No questions, sir.
All right. So
Over.
homework tomorrow. What time did we say homework was going to be? 9 a.m.?
9.
Okay.
So for the homework, would it be all the units we saw today?
Yep. So 1 alpha all the way through 2 alpha.